Hello everyone, my name is Xiaoyang and I come from the University of Chinese Academic Science. It is my honor to have the chance to share my work at SPAA conference. And today, the topic is communicational bonds or convolutions in CNNs. Since this is a brief announcement, I'll quickly share with you the core of the paper. As we all know, the convolutional neural network is developed rapidly in recent years, and it has affected every aspect of people's lives. There are Face ID, voice assistant, language translations, automatic driving, and countless other applications in which CNN plays a vital role. For the convolutional neural network, the convolution operations occupies the main calculation as shown in the figure below. So convolutional optimization is crucial for CNNs, and this is also the focus of our work. As mentioned earlier, the applications of CNNs are everywhere. However, mobile terminals have a high demand for energy consumption of the models. As shown in the table below, data movement consumes a lot of energy. Hence, avoiding redundant data movement is meaningful. Although a small part of the work pay attention to this problem, we are the first to propose a unified theory applicable to different convolution algorithms in CNNs. This theory can not only help analyze the communication of different convolution algorithms, but also help to design data flows close to the lower bound to maximize the data reuse, thereby improving computing performance and reducing unnecessary energy consumption. Our work is based on the red-blue Pebble game, which is a classical I/O complexity research model. The rule of the game and how to determine the expectation are given below. What we need to make clear here is the meaning of several symbols. The J represents a graph and the S represents an expectation. V is vertex of J and Vi is subset of V. Definition of dominant set and the minimum set are shown in property 2 and 3. However, as we know, red-blue Pebble game is for a single-stage algorithm. For convolution, the algorithm usually contains multi-stage. As we know, for multi-stage algorithms, the subcomputation is communication optimal. Does not mean the global solution is optimal, such that the greedy algorithm. Therefore, using the original red-blue Pebble game model directly does not work. We know that if we know P, we know the Q. So due to the time constraints, the process cannot expand in detail here, and we only put out a few definitions and theorems. And the definition 1 is on screen. By definition 1, it is clear that any sequence of subcomputations can be represented as a multi-step computation of the data for the total computation. If we can estimate the intersection of Vi and Ui by using property 2 and 3 in the definition of expectation, the upper bound of Vi is also to be obtained. Donate tilde Oj as the output set of Uj, and tilde O super I sub J as the subset of tilde Oj subset for any V belonging in tilde O super I sub J, and paste from the input set of vertex set to vertex V has at least one vertex, which belongs in the name of all the sets of the intersection of Di and Uk, which K is from 1 to J. And level 1 and level 2 is shown on screen, and I will not read it. It obviously that the dominant set Di can generate Vi. Furthermore, if U can generate U prime, we can find the U can also generate any vertex on every path from a vertex to U or U to a vertex in U prime. For any vertex set U, whose dominant set D and minimum set M contain at most S vertex respectively. Donate set D as the vertex set, which is generated by D. And here, let tilde phi JUK and tilde psi JUK be expressed as follows. It is clear that third 5G and third PCG are cooperating to the number of the vertex generated by D in the intersection of U and UG and the intersection of U and third UG respectively. We define the 5G key and the PCG key as follows. Then 0, 1, and 2 can get. 0, 1 gives us an outbound of Vi, and P can be got by the outbound of Vi and the total number of V. With the 0, 1, and 2, we can estimate the lower bound for convolution algorithms. Here, we take direct convolutions as an example. The deck of direct convolution algorithm is shown on the left, and it can be divided into two steps. The step 1 is generated W curl H curl Cin terms by executing the cooperating elements, a product of II with Kg. The step 2 is sum the product terms like a summation tree. So J can be divided into J1 and J2, and the number of the intersection of V enter and V out is easy to be estimated. TS can be got through 0, 1, and the lower bound can be got by 0, 2. With the lower bound, and this is the lower bound we get, and with the lower bound, the convolution algorithm, we can decide how to schedule the date block to make full use of the in-memory date. In this case, when x prime y prime is equal to zw curl h curl, data movement can close to the lower bound. And in this brief announcement, we contribute the following points. First, we established a data movement lower bound for a composite algorithm which consists of several subcomplications. Then, we established the communication lower bound results for convolution algorithms in CNN. And finally, we designed the near communication optimal strategy. And this is my brief share. Thank you for listening.